Hi, this is Brianette from HowRadiologyWorks.com. If you're new here, consider subscribing below and click the bell icon if you want to get notified when we release new content. Today we're going to talk about X-ray generation and specifically the technical parameters that are involved in X-ray generation. So what we're talking about is the technical parameters of an X-ray tube, and we had another video introducing the X-ray tube at a high level, but we have a cathode where the electrons are boiled off. The electrons are pulled here across this positive potential from the negative to the positive. They hit that anode, they interact with that heavy metal via Bremsstrahlung and characteristic interactions that we talked about there, and then out come the X-ray beam. But what we want to talk about today is the kVp and the MA in this X-ray circuit. And those are the two main parameters that we can change to influence the way the X-ray spectrum looks and the X-rays interact with the patient. So the kVp is the tube potential, so that's the difference between the cathode and the anode in terms of tube potential. So what's the difference in how positive or how negative across this cathode to anode? And the analogy that we use is if you have a waterfall, for instance, like here, in the waterfall, the potential that that water has when it's at the top of the waterfall, that's related to the height of the waterfall. So the height in the waterfall, it's analogous to the tube potential across here. So if you're familiar with the battery that's in your car, 12.6 volts, and the tube potential that's across here from the cathode to the anode in an X-ray tube, that's 30,000 volts to 150,000 volts. So we use the kilovolts to talk about units of 1,000 volts so that it'll be simpler. So a mammography tube would be down in the 30 kilovolts, and a CT tube would be up to 150 kilovolts on the higher end. And then that's the tube potential. And then the MA, that's the rate at which the electrons are flowing. So in the waterfall analogy, it's if you think about the flow of water, so the volume of water per unit time that's flowing down from the top, that's the rate. So if you could control the amount of water that's coming down, that would be the same as controlling the tube current here, or the amount of electrons that are getting pulled across from the cathode to the anode. So we'll talk about how those affect the X-ray spectrum that's generated in the next couple slides. But just we wanted to provide a high-level analogy if you're more used to thinking about things like waterfalls rather than X-ray tubes. So as we talked about before, these are plots of the X-ray spectrum. And the X-ray spectrum is, you can think about the combination of the Bremsstrahlung, the characteristic interactions, and then the filtration that occurs, the inherent filtration and the filtration that occurs along the way before the X-rays exit X-rays exit the window, and then potentially there's pre-patient collimation as well. So this is the X-ray spectrum, where this is a plot in energy on this axis and the number of photons here. So if you change the tube potential, you actually change the whole look of this X-ray spectrum. So this is a plot for 80 kVp. And as we talked about, this is the units here in kEV. This is energy units in kEV. And the maximum kEV is 80 kEV. And that can be achieved because the potential across there is 80 kVp here. And then in the case that you change to 140 kVp, you can see now we have a higher maximum potential. And then the volume under here is also much larger. So there's a very strong dependence on the kVp. And it's a power law in between 2 and 3 in terms of the order. And then if we look at the MA, on the other hand, the MA is just linearly dependent. So it's just the shape of this curve is the same, and we're just scaling it up and down. So it's the same thing as that waterfall if you think about just pushing more water through at the top. In this case, the shape of these curves are the same, and we're just scaling them. So the exposure here is less strongly dependent than in the case of kVp. It's just linearly dependent on the MA. Also, just for completeness, we'll talk about time. When you do an exposure on the X-ray tube, you turn that X-ray tube on and you have that exposure on for a given amount of time. And if you leave the kV and the MA constant, then the exposure is also linearly proportional to time. So the longer that the X-ray tube is on, the more exposure and the more dose the patient will receive. So again, at a high level, the takeaways are that the kVp and MA are the two main technical parameters. The kVp is the tube potential, and it modifies the shape of the X-ray spectrum and dramatically changes the number of X-ray photons that you get. So it goes like more than a power of 2. As you change the kV, the number of photons goes more than a power of 2, so more than the kVp squared. And the MA goes linearly. So the shape of the X-ray spectrum will stay the same, and the number of photons will just scale as you change the MA. Thanks again for watching. Again, this has been Brian Nett with HowRadiologyWorks.com. Let me know what your favorite part about the X-ray generation process is. Is it the boiling off of the electrons, or electrons hitting the heavy metal, or what? Just the fact that bremsstrahlung is a pretty cool word. So also head on over to HowRadiologyWorks.com/XrayGen. That's X-ray and then GEN for X-ray generation. You can download a PDF cheat sheet that has just in one place the information that you need about X-ray generation and the X-ray tube. Again, thanks again.